be a fair price to pay for the single raffle ticket. And so that's where we kind of ended yesterday. This lottery down below, it seems to be, at least the way the payouts have been represented in this chart, it seems to be represented in a slightly different way. It's okay though. I mean, it's certainly okay to write it this way too. Can you guess, for example, what the price of a lottery ticket is in this lottery? It's not a given. It's not a given, but it looks like maybe the ticket price is the lottery ticket price is $5. Do you see that? And the payout, if you win, is what? Do you think?
200.
Yeah, 200. So do you see what we're recording here is like your net winnings. That is, if you pay it for a ticket and don't win, what are your net winnings? Well, negative $5, right? And if you do win $200, then you've really only won $195 if you paid $5 to play. So that makes sense. So go ahead and now solve the problem if you understand what we're talking about here. And I'll have someone come up in a minute and write the answer up here. How about you just tell me from a distance when you get it? And all right.
I know what Q is.
Good. You found Q already? Good job. Find out.
Why? Negative 5.
Have you finished?
I got negative 4.8. So did I. Oh my god, the lottery is a rip-off?
Give me another 20 seconds to think about it, and then Theo's going to give us the answer here. Not yet. Are you sure? Do you know how to do it? Maybe? Okay.
I don't know. One problem. The above thing, you need to take the cost out of the prizes, which would change the fair price to pay.
No.
Why not?
Try it and tell me what happens.
Math stuff, I'm pretty sure.
No, try it.
But I don't want to. It's gonna be a headache.
Well, then stop complaining. All right, let's. Did you make progress, Theo? No? Okay, that's okay. All right, let's hear from. How about? Where is? No, Cassie just got back though, didn't you? You didn't think about this yet. How about Anna? Tell us how that went for you. Yeah. Tell us the answers to both of these. How do you do this? Okay. So, is this the lottery you'd like to play? Are there any lotteries you'd like to play?
Yeah, not really. Well, unless they have a virtually guaranteed.
There are no such lotteries, I'm afraid.
Yeah,
What'd you get?
It's called robbery.
What'd you get? Annabelle, did you get it?
Negative 480.
And what are we talking about here? Negative 4.8 what? Right, so someone interpret this for me. Listen. What's going on then? What does this have as our meaning? Do you want to talk about what this means then for our lives? Yeah. Per play. in the long run, there's never a single play where you'll lose 480, right? That'll never happen. But in the long run, you expect per play to lose 480. That's like significant. That's really bad. It's really bad. Canberra first.
Is there another way to do the bottom? The way I did it was that you could say, assume that there are 1,000 people going in, they're each paying $5 for it, so you know that $5,000 are already being lost and only two are being used. Would that way work in general?
Yeah. The only thing that you have to be cautious about is that if the probabilities are not as easily represented as fractions, which I guess you could always do that, right? Even if it was like represented as like 0.5378, you could be like, okay, well there are 10,000 people and 5,378 of them. You know, so I guess in general the answer is like maybe yeah. I guess maybe you can. Yeah. It might just be like a headache because like what if I say like a third, and then like one 1,000th, and then you're like, okay, well now the common denominator for all of them is, and then yeah.
I know an easy way to interpret this. If you made a business off of this, you would make a lot of money very, very fast if people are stupid enough to not do the calculation.
Yeah, and people are generally stupid enough to play the lottery. That's you would That's
Yay, free money.
Yeah, it's probably very reasonable actually. This is probably what does happen in the lottery. And someone says, oh, actually, you know what? My uncle played once and won $200. And
how many tickets did he buy?
And you're like, well, that is pretty good. $5, and he won $200. So that's a pretty selective story, you know.
In addition,
I don't know. Do you have people in your life who play the lottery?
Oh, but
It may, for those people, it may be time for an intervention, like a mathematical intervention, right?
By the way, the lottery needs to be about like $300,000-$400,000, given the probability somebody else also wins the jackpot.
Okay.
To be worth.
All right. Let's bring in one more idea for our vocabulary, for our calculations, to help us describe a probability distribution, because I think we've already seen that all probability distributions are not equal. For example, like let's say that I get a 100 and an 80 on my last two tests. My average is a 90, and let's say you get a 91 and an 89 on the last two tests. Your average is also a 90, isn't it? But see, the average or the mean really doesn't tell the whole story, does it? So we'll say more about this as we do our statistics unit. But we'd also like not just maybe like this measure of where the center of our distribution lies. We may also want to have, in some sense, something a number a figure that captures the spread of our distribution. So that's exactly what this idea of variance captures. And it's actually a good word to use in English, not just in math, to describe the variability of a data set. So in the case of the grades I was just talking about, I think you might be able to say, yes, we have the same average. But mine, I have a much more variation in my scores. You have more consistent scores, you might say, something like that. Which is a great way to say it, and the thing we want to talk about. So the variance captures that in a number, and it's captured in a way that you might expect. There are some nuances we need to discuss in this formula, and I know it looks complicated, I promise I'll explain. But if you want to calculate the variability of your data, wouldn't you find the mean? And then calculate how far away things in general are from the mean? That is in fact what we're doing here. Unfortunately, if you just calculate the average distance things are from the mean by taking numbers that you get and subtracting the mean, sometimes you get positive and sometimes you get negative things, yes? And when you average those, you get 0, yeah. So we have a little bit of an issue there, because then that's not very meaningful. Like the average distance away from the mean is 0, well that doesn't really make sense. It really doesn't help us describe the variability of the data at all. So we need to make those distances between the data values and the mean that we calculate positive. And the way we're doing it here is by doing what? Well, you could do the absolute value, but what are we doing here? Can you see it in the formula?
Squaring stuff.
Yeah, we're squaring them, which does have the consequence of making them bigger, but it does do what we want, and that is make them positive, right? All right, so yeah, let's say what this means here. We got some symbols to explain. The mu, did we use that yet? No. It's explained down here, but the mu, that's the Greek letter mu. It's a lowercase Greek letter. That we're going to take to mean mean. Mean starts with mu. Okay. Yeah. So in the context of statistics or probability, we use mu to represent the mean. So now you have another symbol for it. Last night we were using e of x to represent the expected value, but mu also works. Okay, those mean the same thing. The other letter up here is the sigma. Okay, that's a Greek letter, lowercase Greek sigma, and that stands for the standard deviation. Sigma. Standard deviation starts with sigma, right? Right? That makes sense. The letter choice is good. Okay. Do you like it? Is that a good explanation? I don't know. From yesterday, I know this looks intimidating. We haven't really talked about sequences and series yet this year, but I think that this makes sense after yesterday. All we mean is just take all the squared deviations and find their expected value, right? That is, multiply by the probability and add them up, right? For every value in the distribution. That just means add them up, right? This should look familiar. It's the same notation I used here. Where is it? There it is. Right? This is just a shorthand way of writing all this out, right? Take each value and multiply by the probability. Take each value and multiply by the probability. So the same thing here. But in this case, instead of take each value and multiply by the probability, take each squared deviation and multiply by the probability and add them up. We'll do this in a minute, okay? I promise. So that calculation gives you something called the variance. Taking the square root, this is just vocabulary, it's not mathematically super significant. Taking the square root gives something called the standard deviation. Which then, by taking the square root, you kind of adjust for the fact that you've taken the thing and squared all the values, right? It's not perfect, but it does at least recover the units of the original data. If the original data was in dollars, the variance is measured in like dollars squared. That's like a little weird. So at least standard deviation then will be measured in dollars again. That's good. That's good. All right, and then one other note about both the expected value and the variance is that they obey the following two properties down here. Let me ask you this. I think all of these actually seem intuitive. They're very compactly written. I'll give you that. But if I just take a bunch of data or probability, some probability distribution, and I take all the values and shift them up by 5 or something, this I take all of your test scores and shift them up by 5. Instead of having a 100% and an 80%, now I have 105% and an 85%. What happens to the average if you take all your data and add 5 to them? It also goes up by 5. I don't think that's rocket science. In fact, you could stop and prove that algebraically. It would be pretty quick. I think you could do it. Okay, next question. What happens if you scale all the data? Another thing that I think you would expect to happen. That is, you take all your test scores and you multiply them by 5. What happens to the average? Yeah, it also gets multiplied by 5. So no huge rocket science there, I don't think. In one statement, it's saying both of those things here. Do you see that? We're saying that if you multiply your data by a number and add a number to it, or do one or the other or both, right? Then you can just, if you want to know the new expected value of your data, it's just the same as the old expected value of your data, just transformed in the same way as each of the data values was, right? So that's not a huge surprise. Let's talk about why the variance also maybe intuitively makes sense. What happens if you take your data, all your test scores, my 100 and my 80, and let's say I shift them down by 20 or something.
Why?
Talk to me about the variability of my scores. The variability of my scores hasn't changed at all, even after a translation, right? Really, I want to change like the shape of my distribution if I want to get at the variability. So that's exactly why you see over here, you might be thinking it must be a typo. Where did the B go on the right side? Doesn't that matter? And the answer is no, it doesn't matter. And it's for the reason you just thought of that, right? If you translate your data up and down, that doesn't change its variation, right? Good. Now, multiplying and scaling your data by a number, that will change its variability, won't it? So if you're talking about the variance, because it's squared, everything up here is squared, then it will scale by the variance, will scale by the squared value of A. The standard deviation will scale by A. Okay, so, good. Let's actually calculate, let's actually go through and try and see if we can interpret this formula up here now. Because some of you are still like, sounds good. Not really quite still sure about what this formula means. So let's go through and do it.
I find the one on the right most section to be easiest to understand.
Yeah, I mean the one on the right is just saying what we said here. It's just the expected value we did before, except not of the values, but of the squared deviations.
And it's not as unsightly.
It's not as unsightly. Have you seen this probability distribution before? Yes, you have. We did it early on. I think this one distribution I asked you that on that day. Is this a probability distribution? You remember doing this? You add it up, you figure out, does it add up to 1? All that. So let's write it out. This part is not meant to be the news. There's no surprise here. Here are the possible values in our world. And here are their probabilities, apparently, right? From the function. Now, do they ring a bell? Do you remember this? Okay. All right. So now let's actually do what we said we would do. For each value, we're going to do what this column here says, right? We're going to take the value and subtract the, oh wait, hold up. What do we still need to calculate maybe before we get started? We're going to make these computations. We don't currently have mu, do we? So let's do that first. It does say to do that, so let's do that. Can we all calculate the expected value in the way that we've been doing? Try to do that. I'll do it too. You do it, we'll all do it, it'll be fun. Get your calculator out if you don't have it out already. And go to Stat, Edit, and in L1, this is like your little very own little spreadsheet world. 3, 4, 5. Put your values. In L2, put your probabilities. 4 out of 62. 8 out of... Yeah. What's wrong? I don't know how to, I don't know how to do yours. Do you have your manual?
No, I don't carry them.
You should calculate your
I don't even know if I still have it.
You're carrying a weapon and you don't know how to use it?
It's not a weapon unless you throw it at somebody, Mr. Chase.
You've never seen me use a calculator, have you?
Have you done it? Have you figured out how to get to stat edit and enter in L1 and L2 the values and the probabilities? Okay.
We did it in practice.
So let me show you some spreadsheet technology in your calculator. Are you ready? So go to L3. Go to L3 and press enter. And make sure you're down here and it says L3 equals blink, blink, blink. Do you see that? Make sure it doesn't say L3 of 1 or 0 or whatever equals blink, blink, blink. Make sure it says exactly what I have. And then I'm going to do, why am I doing this? L1 times L2.
So it is Excel.
Right? So I'm taking L1 and L2 and I'm multiplying them. Well, why would I do that? Why would I do that? What am I about to do then? Add them all up. Isn't that what calculates the expected value? So there's a feature on our calculator that does that too. So go to second list. And if you go to number 5, sum, L3, there's the mean. Here, we'll store that in M for later use. There we go. Did everyone catch that? All right. So that's the mean. Did you get 4.16 too? Okay. That's the expected value, right? Each value times its probability. Sum them up. Well, the 62 is already kind of in there, right?
I have it. On my calculator.
Yeah, let's talk about 1-bar stats now too. All right, ready? So if you're, I don't know where you are. Are you on your home screen or something?
Yeah.
So go back to your home screen, and then go to Stat, Calc, 1-bar stats. Now if you have a new calculator, you're going to put in L1, and in the frequency lists, you're going to put in
Wait, it says number of lists.
L2.
Wait, is there only one list?
Did you put it? There should be 2 lists. You put in L1, 1, 2, 3, 4,
I
5.
said one variable statistics, and it says number of lists, and you can change the number.
Yeah, you want, I guess you want two. I don't know. I don't know what your calculator is. I don't know.
It
Anything.
says the number of lists, how many lists are there?
Maybe 2? I don't know.
No, but I didn't use the calculator.
I don't know about yours. Alright. If you have one of the older calculators, you might actually have to type in 1-bar stats L1, comma L2. Try that. Okay? So when you hit calculate, notice that, do you see the mean there? So you go to stat, cal, 1-bar stats, and then make do L1, L2 for the frequencies. So do you see that they give you the mean just right off the bat? You don't have to use L3 then. In fact, here, let's just kill L3 right now. All right, so we got the mean at 4.16. Next. Let's talk about how to get the standard deviation. We said, now pay attention. We said it's going to be the value. Now notice I'm going to L3 again. The value from L1 minus the mean, which is 4.16, right? Actually, you know what? You want the whole value for the mean? You can actually go get the mean we just calculated here. You can just type in 4.16 too if you want, that's fine. And then square it, isn't that what we're doing? Cassie, you have a question.
Why did you put in 0.6?
What's the standard deviation on that list? Wait, what?
No, that's because I didn't hear it saying stats for asking if 1, 2, 3, 4, 5, 6.
No, I think it was 1, 2, 3, 4, 5. Yeah. Alright. Are you watching what I'm calculating? Let's go back to the screen here. Aren't we supposed to calculate the value minus the mean, 4.16, squared for each one, squared, times the probability, 2 over 62 for the first one, right? So do you see why I'm typing in what I typed in for the definition of L3? And then I'm going to press enter and it's going to calculate that list. And we're just going to sum that list. Yeah.
So when you did 1-bar stats with L3, like what you count?
We did 1-bar stats with L1, L2.
Oh yeah, L1 and L2.
Yeah.
Doesn't it only give us the standard deviation? Could we just square that?
Yeah. But we got to do it once by hand. Come on, you're killing the party, you know? Like. All right. So here we go. And then if you sum those guys, where is it? That's the variance. Do you see that? So let's write that here just to make sure we get this here. Okay. So we got for each of these. Now keep in mind that you want to use maybe a more precise value than I'm going to write for the mean here. So we're doing 1 minus 4.16 squared times 2 60 seconds. 2 minus 4.16 squared times 4 60 seconds. 3 minus 4.16 squared times the probability. 4 minus 4.16 squared times the probability. Does this make sense? This is what we just had our calculator do very quickly for us. And then adding those up gives the variance. So the sum of those things is apparently 1.1. 1.16? No. 1.168 or something, wasn't it? Approximately. Oh, alright, so that's what we got on the calculator. And we didn't write it down. We should also write down what E of x was, right? We already calculated it. It's mu. It's 4.16. Alright, so we did it. This is the variance. And this is the expected value, okay? Now it is also true for those who noticed, and for those in stat, right? Both of these things are immediately on one of our stats. And as my note says at the bottom of this, there's never a time where I will make you do this again. You can always ask your calculator. So let's just run one of our stats one more time. Notice that if you don't have anything in L3, that's perfectly good, right? We just want L1 and L2. So we're going to run one of our stats again. And notice there's the mean. Where's the standard? Where's the variance? Well, it's actually not there. But the standard deviation is, it's 1.08 apparently. 1.08. In fact, we can get that. It's under stat variables. Is that what we got? 1.167? Is that what we also got by hand? Okay. So you can always do that on the calculator too, okay? Which one? Oh, you go to vars? Just like when you go to get Y1 or something, you know? You go to vars and then statistics variables. And all those variables will have currently the value they last had when you did one var stats, right? Yeah, you do. I would have to Google like you. Google how to do one var stats. I know you're right. I need to know how to do this. I need to own one first. I've never even like touched it. Have a great day, guys. See you tomorrow.